Okay, so welcome to Math 389 Advanced Analysis. And so what I want to do today is just finish the conversation on random matrix theory. And so in particular, this means evaluating the contribution of non-crossing matchings, which we've done most of. I want to show a little bit that crossings won't contribute. I don't want to do a full, painful proof of why the crossings will never contribute. I want to just do enough so that you can walk away with an understanding. And then a huge slew of research by my students has been to look at matrices with special properties and see how that affects the distribution of eigenvalues. So we'll explore a little bit some additional structures you can put on and the impact this has. And what's nice is this talks a little bit about how we move from reading mathematics to doing mathematics, to creating something new. What do you start with? The reason we consider Toeplitz matrices is, yeah, I don't mind recording this, is I was running a summer RU with some colleagues in California, and I had funding to bring a couple of students to a conference in Honolulu for a few days, including Professor Goldmacher. And I had to leave some students. I couldn't bring everybody. So I left some of my students in California, which is not a bad place to be left in the summer, and took the rest to Hawaii. And when I came back, one of the people I had left had been working on Toeplitz matrices. I said, okay, well, why do we look at the distribution of eigenvalues? And he'd been looking at Toeplitz matrices for something completely different. And it turns out we were getting some interesting results, and we were curious if anybody else had ever looked at it. And so we started asking the mathematics community, and after a couple of weeks, the answer finally comes back to us. Yes, someone else is looking at this right now. They're actually less than 2 miles from where you are. And it's just sometimes weird when a problem becomes ripe, when multiple people start to look at it. When are the tools ready? When are people at a point where they're going to ask the question? And how do you find out who else is doing this before the paper is published? We found out in enough time that we could make sure that the papers did have some differences. All right, so we want to evaluate the contribution of non-crossing matchings. And so we showed earlier that the number of non-crossing matchings is the Catalan numbers. And the way it works is we have a bunch of vertices going around dot, 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 dot. And so what was nice is we could say, well, look, without loss of generality, this has to be matched with somebody. And then everybody here, it has to be non-crossing. And then everything here has to be non-crossing. And what we want to do is we want to lift to the easiest possible case we can study. So the simplest is when n equals 2, we have ij and ji. Well, there's only one way to match them. And so the term we get is aij, aji, that's aij squared. It's going to contribute 1. All right. Things get a little bit more interesting now when n equals 4. And now we'll have ij, jk, kl, li. And when we match things in pairs, there's 2 ways to match things in pairs without crossing. I can go like this, or I could do the reds. Do you agree that the 2 cases are the same? By symmetry, if I can do one, I can do the other. So in this case, the j's are the same. So what does this imply? So this implies I equals k. And then if I equals k, L is free. So here j is free, and here L is free. And we will get aij squared, il squared. And everything is going to contribute fully. And so when we look at the number of pairs, we get I, J, and L are free. So we'll get n cubed pairs. And here, I is free, we get n pairs. All right, let's look at 6. So we have ij, jk, kl, lm. Will you allow me to do an abusive notation? Mn, and then actually ni. So we'll do n in quotes equals 6. So how many ways can we match in pairs? So we could do something like this. And how many configurations would we have like that? 3. We could have ij matched with jk. And now if we're matching with pairs, we could do it like this as well. How many would there be like that? 2. We could also do match like this. So is that the same as the first one? Just rotated. So is that new? So that is not new. So is there anything else other than these 2 possible configurations? But non-crossing. So everything else is going to have a crossing. So if we start to look at what's going to go on in this case, let me just copy this so we can do it twice. So in this case, oops, and the other case would be like this. So now, as we start going on here, where do you want, on the first one, which do you want to analyze first? The ij with the lm, the jk with the kl? Yeah, because we've got an adjacent matching there. And so we know from this one, this is going to force j equals L. And now, since j equals L, this is really the same as jm and ij. So now from this we get I equals m, or m equals I. And now this becomes in, ni. So that we get that for free. So now, what are the free parameters? So I is free, j is free, k is free, L is fixed, M is fixed, N is free. So that's going to be something of size n to the 4th. If we look at the other one, now ijjk, so this is going to give us k equals I. So then this becomes IL, LM. So this is going to give us m equals I. And then IN, NI. Okay, so what's free now? So I is free, J is free, K is free. Nope, K is determined. L is free. And N is free. And that's also going to give us n to the 4th. So what we've seen here is all the possibilities. Then there's no obstruction in the counting. Everyone is coming in full. Do you think this is always going to be the case? So I've sketched drawings up to 6. So the key fact is there always going to be an adjacent pairing? Because with the adjacent pairing, you can lift one of the indices as free, and then the other 2, so we can here, we lift K, and then the J goes to the J, the L goes to the,
Probably at least two adjacent pairs. Yeah, you have that those.
that seems reasonable,
Because we divide the first division
Right,
into
right.
two parts.
right? Yes. And so the idea is, and again, it's a question of how carefully do you want to write this up? Is there must be an adjacent pair. And once we have the adjacent pair, we can lift one of the indices out as free, and then it's now we've reduced it to one smaller. And so by induction, we're done. So all of the non-crossing configurations contribute fully. Now, the number of non-crossing configurations is the Catalan number. The number of matchings and pairs is 2n minus 1 double factorial. 2n minus 1 double factorial is much larger. And so the question is, what happens to the non-crossings? So the ones with crossings. So what I have written to do is show crossings don't contribute in some cases, rest is left for the reader. So I have to choose a case. What case do you think I'm going to choose? N equals 4, right? It's the first case when I have a chance. And so we'll take n equals 4. So ij, jk, kl, li, and we will assume we have a crossing like this. So let's see what this tells us. So now we know ij equals kl or lk. And the other one is jk equals li or il. So from the first, this gives us I equals k and j equals l, or I equals l and j equals k. Well, for the second, we get j equals l and k equals I, or j equals I and k equals L.
I think if we were to solve this without knowing that this is Catalan secretly, we would do something like, for example, consider n equals 6. Then we know that there must be at least one adjacent pair, and there are 6.
Well, no, because if we do 6, I could have a pairing like this.
Oh no, I'm talking about not crossing.
Okay.
Non-crossing one. So if we have 6, we know that there must be at least one adjacent pair, and there are 6 adjacent pairs we can choose from. Okay. Assuming that all, I mean, do we count up to symmetry, or
It depends how you want to do things.
if we don't have
You have to, I mean, at the end of the day, you have to consider all matchings. That means you do have to take into account symmetry. But you can say, look, without loss of generality, these 3 configurations will all contribute the same. I can just do this one.
I think it's easier to do without considering symmetry. So if you're saying, okay, I have 6 choices of pairs that I can shave off the
Right.
figure, and I say 6 times, and we're left with this n equals 4 case, right?
Right, I mean, that's the main idea is as long as you know there's an adjacent matching, you can remove one of the variables as free, the others push out, and now you've just reduced yourself to a previous case. So I think we agree that in the case when we have no crossings, it's not bad. Let's look at this case with crossings. So how many possibilities are there right now that we need to look at? Worst case, how many possibilities? 4. That's not that bad, right? So we can call this, 1, 2, 3, and 4. So if 1 and 2, then we have j equals L, I equals K, So only two free parameters. So that's order n squared tuples, but we divide by n to the n halves plus 1 is n cubed. So it doesn't contribute. If one, oh, not 1 and 2, this would be 1 and 3. If 1 and 4, so we get I equals k, j equals L, but then L equals k. So L equals k equals j and j equals I, all the same. So all same, only one free parameter, order n. By symmetry, I want to say I don't need to consider the other cases. Because since I've done, I can always just rotate things.
Yeah.
Right? By symmetry, 2 and 3 and 2 and 4 are the same. So really, there were only two things to check, and we lost a degree of freedom, or we lost more than a degree of freedom, but that does still mean we lost a degree of freedom. So no matter what, we don't have enough to contribute. So if there's a crossing, we have some problems. But this isn't a really simple case. Maybe something happens as you go further. Years ago, I mentioned the conference I took some people to. And so that was the summer Professor Goldmacher was working with me. And I believe that was when we were looking at weighted d-regular graph adjacency matrices. So for a d-regular graph, every vertex has exactly d neighbors. And what you can do is you can write down the adjacency matrix. And so d-regular graphs, Aij is equal to the number of edges from I to j. And so we'll do a situation where we don't allow ourselves to have multiple edges connecting two vertices. You either connect them or you don't. And so when I construct my matrix, each row sums to D. And we'll assume AII is always 0.
This is an undirected graph.
It's an undirected graph. Now, in the real world, you might want to allow some of the AIJs to be greater than 1. Maybe it's really important that the President of the United States and the Premier of the Soviet Union in the Cold War can communicate. And you don't want to have only one line. Oh, damn it, busy signal, right? So you might actually want to allow multiple things. If you think about what happened a year or so ago when a boat got stuck in the Suez Canal, it caused a lot of trouble. So we often want sometimes maybe multiple ways, but it's a little bit redundant to be using the same cable to connect the same thing. So you might want to just have a graph that's well connected. So if something goes down, you can reroute with a small cost. And this is similar to the paper I sent you from Quanta, which was talking about some remarkable breakthroughs in the eigenvalues of these matrices. So what Professor Goldmacher and I did is we looked at these matrices, and it turns out that they have a different distribution than the semicircle law. As D gets larger and larger and larger, it converges to the semicircle. So in the limit, as D goes to infinity, it becomes semicircular, but for small d, it's not semicircular, and you can write down exactly what it was. So my idea was, well, what if we nudge these adjacency matrices a little bit and help them? So rather than putting down a 1, what if we put down a weight wherever there's an edge? And the simplest case is all the weights are 1, but what if we draw the weight from a probability distribution? Is there a probability distribution we can choose so that the resulting adjacency matrix, that the distribution of its normalized eigenvalues converges to the semicircle? Well, that's a hard problem. So what we did is we said, let's try to calculate what the first few moments of that distribution have to be and see if we recognize it. And so we were able to calculate the first 7 moments of what we needed the weights to be to get to the semicircle. Anybody want to guess what those first 7 moments were. To get the semicircle, we should weight the entries by the, yes, which we found very surprising.
That's interesting.
Now, when I say we calculated the first 7 moments, I'm putting things in as good of a positive light as possible. We really only calculated the first 6 moments. We knew the distribution was going to be symmetric.
Yeah.
So you get the 7th for free. The 8th moment is not the 8th moment of the semicircle. Really. It's something where when you only have up to degree 6, I'll send you all the paper, there's not enough freedom for some new features to emerge. But once you go high enough, and you get a correction factor of 1 over d squared. In the limit, the correction factor goes to 0, but it's there. And so you have to be really careful when you look at small things. It's possible to be misled. It's possible that you're not seeing the truly generic behavior. One of my favorite examples is if I tell you in the last 4 games, you have 3 wins and a loss. That's a 750 winning percentage. That sounds like the team is playing really well. Assuming that the person who says this is not a mathematician, but a normal human being, what else do you know?
What was the last one?
So we have, let's put in boxes. This is 1 game ago, 2 games ago, 3 games ago, 4 games ago, 5 games ago. We know in the last 4, there's 3 W's and 1 loss.
Assuming they played more games than 4, their 5th one was a loss.
Right.
Their 4th one was not a loss.
And the 4th one was not a loss.
And probably the 2nd one was a loss. Or the first or 2nd one, the most recent one was a loss, because they want to count the 3rd.
Right, so if the 3rd was, so probably this is a win. But we know it's got to end, win-loss, because I want to keep going and including as many wins as possible.
Yeah, unless the season just started.
Unless the season, so really, if you look at the last 3 games, they're 2-1. If you look at the last 5 games, they're 3-2. They're basically a 500 team. But if I talk to you at just the right moment, I can make them look a lot better. And so you've got to be careful how the information is presented to you. Is it can be presented in such a way as to be a bit misleading. And that should in every way be taken as a preamble to the next part of today's lecture. So let's consider the Toeplitz matrices I mentioned. So they're constant along diagonals. If you want, you can assume that B0 equals 0. Because all B0 does is it translates all the eigenvalues by B0. So as long as B0 has mean 0, its effect is going to just be to spread out the eigenvalue distribution to increase the variance. It's not going to do anything to the shape. So this really has order n degrees of freedom. And again, this is now we're moving from learning math to doing math. A real symmetric matrix has order n squared degrees of freedom. This has order n degrees of freedom, but in a very structured way. Maybe it has different behavior. Another type of matrix people look at is they look at band diagonal. So maybe you have R bands above and below the main diagonal where your entries are freely chosen, and then everything beyond that is 0. And when you look at the band diagonal, if the band has length 1, just the main diagonal, then whatever distribution you choose the entries from, that's the distribution of the eigenvalues. It's not going to be semicircle. It's, if you choose them from a Gaussian, it's a Gaussian. If you choose them from a uniform, it's a uniform. As the number of bands increases, it starts converging to a semicircle. And roughly when you get to about square root of n bands, it looks semicircular. So a lot of times it matters how things are arranged. Here, we have something of order n degrees of freedom, but there's a lot of structure. And so you can show, again, doing the central limit second moment argument, that the eigenvalues are of size square root of n. And you can ask, what can you say about the distribution of eigenvalues? Well, if you're trying to get a feel for the answer, what's the first thing you should do? Try some, gather data, right? Hopefully that's the next slide. It's a little bit down the road. So the next slides are just setting up the preliminaries of the calculations. If I want to calculate the 2kth moment, I look at the matrix elements, they've got to be matched in pairs. And so what really matters is, because it's, symmetric, all that matters is the difference of the two indices. So I look at just the absolute value, and those are going to be my n-1 parameters. And so if I have a matching, I can either be matched without a sign or with a minus sign. So there's 2 to the k possible choices of sign. There's 2k minus 1 double factorial ways to pair. So it's most going to be 2k times the Gaussian moment. I'm not going to go through this slide. This is just basic linear algebra to show that if you don't have everything matched with a minus sign, you end up having an extra equation that must be satisfied, which means you lose a degree of freedom, which means it doesn't contribute. So the only configuration that you have to worry about is when everything is matched in pairs and with a minus sign. So again, it's just a straightforward linear algebra calculation to show that if they don't all have plus signs, you end up having an equation where not all the coefficients in front of the x's are 0. But then the only way this can be satisfied is all the x's are 0. But if all the epsilons are -1, then all the coefficients are 0, and you get no information. So all the coefficients have to be 0. All right. So now here's the numerics. Everyone agree it looks normal? The third moment, I'm sorry, the fourth moment of a Gaussian is 3. The fourth moment is 2 2/3. It's not a normal. Whoops. I wanted to just move that out of the way. Now that you know that it's not a normal, do you see anything interesting? How well do you know the normal distribution? So if you look over here, the decay is not right. Look at the probability around 2 and just how quickly it's dropping off. And again, if you have to really know the normal distribution. The other thing is, and there is a reason I'm doing this. One of my jobs in this class is to teach you how to write well. So occasionally I have to do things poorly. I have done something poorly on this plot. Or 2 things, depending on how you want to define things. I know it's hard for you to believe that I did anything poorly.
Maybe to have a better feel, just normalize the y-axis.
Yes, absolutely. So this is horrible. I'm doing count, not frequency. That's absolutely terrible, right? You should rescale so that you're doing a percentage. And again, you have to be a little bit careful because of bin sizes and whatnot. But you're looking at count data like that. We don't want to look at count data. Okay. So if you really know your normal distribution, when you look at this, you would see that it's not quite normal. We thought that those were just reasonable fluctuations for the amount of data points we had and the rate of convergence. And when we saw this, we wrote Gaussian. And it turns out the other group also wrote Gaussian when they saw this, and they did the same experiments. And we both got stuck trying to prove it was Gaussian. And we even got heuristics from colleagues of ours as to why the answer should be Gaussian. Heuristics were wrong. Not by much, but they were wrong. And again, it's very easy to be misled. It's very easy if you think you know what the answer is to do calculations to get them. At times, I have been disappointed in the background of my students in my classes at Williams. I do not want to be disappointed in your cultural background. Can somebody tell me about planet Vulcan? I'll accept 2 answers. Where have you heard of planet Vulcan? Star Trek, okay, that is one of the acceptable answers. That's where half of Spock's family is from,
Thank you for saving us.
okay? I won't ask where you're from. But yes, so Vulcan, famous in Star Trek, but that's not the first time a planet named Vulcan.
Oh, right, because it was, I'm not sure who that was, but they conjectured that there must be another planet.
So when they were trying to understand the orbits of the planets, I'll try to remember to send the article by Asimov on this. For a while, things were going great. And in the 1700s, Herschel discovered the planet Uranus. And after a while, Newton's laws of gravity were not correctly predicting where it should be. And so they conjectured one of two things. Either Newton's law of gravity is wrong, which we really don't want because it's doing such a great job, or maybe there's another planet further out that's pulling on Uranus, and it's so far out that it doesn't really have that much of an impact on everything else. And they estimated what its mass should be and where it should be. Some of the inputs they used to make these estimates were bullshit, but it ended up giving them about the right part of space to look at. And there was a race to see who could find it first. And unfortunately for Adams, I believe Adams was the British astronomer, he did not get time on the telescopes first. He couldn't convince people to point the telescopes there. And I think it's Leverrier was the first person to see it. And he became a rock star of the 1900s. He predicted the location of the planet with pen and paper, not using any observations. This is before computers. This is before grad students. He's doing these calculations. Oh, with grad students, it's not so bad. You can throw them in the dungeon. Yeah, give them some pizza. We had the leaning tower back then. You could have them just cranking away. So he has this international reputation. Now, the orbit of Mercury was off by a little bit. And if you fix Uranus by adding a planet very far from the sun, maybe you fix Mercury by adding a planet very close to the sun. And if it's of a small mass, it's going to have the greatest impact on Mercury and a much lesser effect on everything else. And so people were happy that there was a proposed explanation, but so we've got to look directly at the sun to see this planet. That's going to be kind of hard. So you have to wait for an eclipse. And so there were only a few times when you had a chance of observing this new planet. And they named it Vulcan after the Roman god of the forge. And most people, when they turned their telescopes, what do you think they saw? Well, you know the answer because I've sent you the article.
The sun.
Yeah, they saw the sun. And most people said, we can't see anything. But a couple of people, either through bad equipment, faulty science, or the desire to be the one to see the planet that is being predicted by this guy who was successful with Neptune. I saw it.
By the sun.
Or by the desire to be remembered. And so there were some sightings, but not enough to confirm. And as time passed and the telescopes got better, they kept reducing the size of the possible planet to the point where now it's most a couple of asteroids and it won't have enough impact. And the solution is that the gravitational field of the sun has energy in it, and energy is equivalent to mass. And when you factor that in, Einstein's general relativity fixes Mercury and all the other small planetary issues. Why am I telling you the story? Because it's so easy to be misled by data. If there's something you want to prove, especially if it's somebody you want to like you, to respect you, to publish your stuff, you have this incentive to see what you want to see. And again, I have a PhD from Princeton. I'm bragging a little bit. I've been a professor at Williams for over a decade. I'm bragging again. I can fill up a lecture with content and theorems. That's not hard for me to do. That's not what's going to serve you well in the rest of life. It's much better, especially since this is a class on exposition, to talk about what really matters. Is you should be smart enough to notice something's a little bit off there. It's not quite a Gaussian. Is this because of a slow rate of convergence, or that something else is happening? Or are we so dead set that we want to see a Gaussian that we're not seeing the data dispassionately? It is very easy to see what you want to see. How many of you have ever watched your sports team play? How many of you are just sickened by how biased those referees are against your team?
They're cool.
Aren't they horrible, absolutely horrible referees? Every single game, every single time, they keep. And it's amazing that you can hear this from both sides. Right? It's really easy when you have a preconception to have that influence you. It is very hard to be dispassionate. I will not say some of the times I have been so dispassionate, people have been amazed because this is recording. I will stop class early and answer some of those. All right, so here are the configurations for the fourth moment. Do we agree that the first and the third are the same?
Yes.
And so now if I want to analyze what's going on here, I have two cases. And so for the first case, I would have B I minus J, and then B J minus K, and these would be matched. And then I would have B K minus L matched with B L minus I. And so we know that the only matching that works is with the minus signs. We would get I minus J equals K minus J. So I equals K, J is free. Yes? And for the other one, we would get K minus L equals I minus L. So I equals K and L is free. So we get I, J, and L are free. That's n cubed tuples. And similarly here, it's n cubed tuples. What about the other one? So now here, we've got B I minus J, B K minus L, and then we've got B J minus K, B L minus I. Yes? Just making sure I've got everything. And JK, okay. And so we need to figure out how many tuples. And so this is our configuration. IJ, JK, KL, LI. And we know they're matched in pairs. We've got them matched. And so here we have I minus J equals L minus K. And for the other, we have J minus K equals I minus L. Well, if I subtract L, I get I minus L. And if I subtract J from the other side, if I add J to the other side, I get J minus K. Gee, these two equations are the same. Okay, so now, is any variable immediately free? So before, when we looked at things before, we could say, J is free, L is free. Is anything free here? Sure, you can take I as free, but then maybe, we don't know this initially, but maybe some values of, maybe there might be no values of everything else that works with that. So right now, it doesn't look like anything is immediately free. So we need to find, so the goal, count the tuples I, J, K, L in 1 dot 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 n to the fourth with I minus L equals J minus K. Give me a crappy upper bound that you know works. Good. So you have learned how to be a smartass, right? It's trivial that n to the fourth works because there's at most n to the fourth tuples. So that's just completely forgetting the equation. Can you do better? Can you do better than n to the fourth? So how would you get n to the third? Yeah, better is n cubed as we can say which do you want to be a free I, j, k, and you want L. So L equals I minus j plus k. So L is forced. But maybe not in 1 dot 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 n. So that's the question. So now, if whenever I choose I, j, k, if L always is in the interval 1, n, then I get n cubed tuples. And that's exactly what I need. And if I get n cubed tuples, then I come back in here, if I put in n cubed, n cubed, n cubed, n cubed, it's the Gaussian. Everything contributes fully. So if that's n cubed, it's the Gaussian and everything contributes fully. If it's less than n cubed, it may still be the Gaussian.
It's not like too small.
Yeah, so what would be something that would still give me the Gaussian but not be n cubed? So we all agree that if I got n cubed, it would be Gaussian. So give me something smaller than n cubed that was.
There was small log factor.
I'm sorry.
I don't know exactly.
So we need to correct n cubed. We need to make it larger or smaller.
Minus a polynomial.
Yeah, minus a polynomial of what degree?
N squared.
Yeah, so n cubed minus n squared would still be a Gaussian. So it would contribute fully in the limit. And so it doesn't have to be just 1 second. Dealing with a bunch of visiting high school kids. It doesn't have to be n cubed. It just has to be n cubed minus small corrections. So now when we look at this, oops. We know it's at most n cubed. Do you think it's n cubed minus n squared? Or do you think it's n cubed minus a multiple of n cubed?
Well, given that you said it's not a Gaussian.
Good, given that we've said that it's not a Gaussian, right? Given that I've told you the moment is 2 2/3, we're already getting a contribution of 1 from each of the adjacent matchings. I'm probably going to lose a lot. So what we need to do is we need to count the number of solutions to I minus j plus k is in 1, 2, dot, 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 n, given I, j, k in 1 to n. So we know that this is at most n cubed. We want to do better than that. We want to actually count it. So there's a bunch of techniques we can do. The first is just let's show that it's not n cubed, that it's actually at most some constant less than 1 times n cubed. So when you look, what is the danger for I minus j plus k? There's 2 dangers.
J is small.
I'm sorry?
J is small.
Good. So maybe, so danger 1, too large, and danger 2,
Small.
too small. How can you ensure that it's too large?
J equals 0, or it's I equal n, j equals 0.
Okay, so if you do something like that, it'll be 0, but it's not going to give you order n cubed tuples. So I want to have a large number of tuples that fail. And so again, when I was doing this argument, I just wanted the simplest thing I could do that would give me a savings. So if I and j, if I and k are really large and j is really small, j is not going to be enough to pull me back to being under n. So let's take I and j greater than or equal to 2/3 n, and let's take k less than or equal to 1/3 n. I'm not going to worry about the case when it exactly balances out. Yeah, this is waving hands. So how many tuples do we lose? How many tuples are there like this? So how many tuples have I greater than or equal to 2/3 n, j greater than or equal to 2/3 n, and k less than or equal to 1/3 n? Why 2/3? The number of tuples should clearly depend on n. How many choices are there for I? Nope. I want I to be at least 2/3 n.
No, 1/3.
1/3 n choices for I. How many choices for j? 1/3 n. How many choices for k? So there's 1/27 n cubed tuples. Now let's make things too small. How could I make things too small? Yeah, I and j are at most 1/3 n, and k, I'm sorry. It's I and, this should have been I and k, sorry, and j down here. So this should be I and k, and then j down here. And j greater than or equal to 2/3 n. So that's at least 1/27 n cubed. So we lose at least 2/27 n cubed tuples. So at most, n cubed minus 2/27 n cubed is 25/27 n cubed. And that's enough to show that it can't be the Gaussian. It's a positive loss. The actual answer is we lose 1/3. Here we lose 2/27. How many 27ths is 1/3? 9. So we've only got 2 over here. But again, this is being really crude. And so we're doing something that works for everything. If I and j are a little bit smaller than 2/3 n, some of the j's will still cause problems. So can anybody think of how would we actually get the answer for how many tuples work? Well, how many tuples don't work? We want to count I, j, k with I plus k minus j not in 1 dot 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 n.
Two equations less than greater than less than 0, less than 1.
Well, what I can do is, let's say I know I plus j. I'm sorry, I plus k. Do I know how many j are bad?
Yeah.
Then the number of bad j is what? We'll assume that this is at least n. So if it's n plus 5, approximately how many bad j's are there? 5 or 4, something like that, right? If it was 8, if it was n plus 8, how many would there be? So the number of bad j is what? I plus k minus n. So if I know what the sum I plus k is, I know how many bad j's there are. And I only have to care about I plus k being going from n to 2n. So count the number of I and J and I and K with a sum between n and 2n. So what if I plus k equals m? How many ways can that happen? And m would be greater than or equal to n. So how many choices of I would work? Does it depend on m? Yeah, if m equals n, are there a lot of ways to do it? Yeah, if m equals 2n, there's only one way. So the larger m is. So once I tell you what I is, k is then forced. So how many choices of A? So once no I, then k is forced. How many choices do we have for I?
And choices for I.
Are you telling me? So remember, m is greater than n.
Yeah.
So it can't be m choices
Yeah.
because there's at most n choices for I.
And choices for.
Inversely.
Well, let's think. So again, when you don't know something, make a table. M number of I. When m equals n, how many choices are there for I? Basically, you can choose anything for I. When I'm not going to worry about the plus one, minus one. Up to plus minus one over 0. When m equals 2n, how many choices do you have for I? 1. And doesn't it? So again, I'm not trying to prove as many theorems as possible. I'm trying to talk about how do you think about things? How do you get to expressions? By looking at it like this, I know there's got to be some kind of relationship. I know as m gets larger, there's fewer choices for I. When I take m equals n, I've got a lot of choices. So maybe the number of I is maybe m minus n. Up to plus or minus 1. I don't worry about that. But does that make sense? Or is it 2n minus m? 2n minus m looks a lot better. When m equals 2n, there's one choice. When m equals n, there's a lot of choices. And you can see that it makes sense. If I have n plus 5 for m, then I could take m to be 5, 6, 7, 8. Any of those will work because I can then add enough because I don't have to add more than n. So there'll always be a k that works. So the number of i's that work is 2n minus m. So number of I that work to get an m in n 2n is 2n minus m. That forces k, and the number of bad j is I plus k is equal to m, right? Is m minus n. So we'll have the sum. We can do it many ways. We'll have m goes from n to 2n. And then once we specify an m, the number of pairs ik is 2n minus m. And then the number of bad j is m minus n. Okay. So let's look at this expression. Any thoughts on how we should do the sum? What should we do? Yeah, multiply it out. This is Henry David Thoreau. Simplify, simplify. Before you start doing any algebra, simplify things out. This is the same as the sum. M goes from n to 2n. Hopefully we haven't made a mistake. We'll get a negative 2n squared minus is a plus mn, and then we have a plus 2mn. So I think it's plus 3mn minus m squared. So this is going to be a bit of a pain. So we would have the sum, m goes from n to 2n. I can pull out a 3n, and we'll have an m inside, right? And then we'll have minus 2n squared times n. And then we'll have a minus the sum, m goes from n to 2n of m squared. Yes? Okay. Can we evaluate these sums? Yeah. So these are not that bad to evaluate. And when you look at what's going to go on, you can see the first sum is clearly going to be of size n cubed. The second is going to be of size n cubed. The third is going to be of size n cubed. And we just have to use the formulas. So, use the sum, let's say, I'm trying to think of what letter have we not used yet. This is a great proof when we have this many letters. We'll use Greek letters. Nu goes from 1 to, I guess V goes from 1 to capital V. V is V, B plus 1 over 2. And then the sum, V goes from 1, we can even go from 0 if we want, to capital V of V squared is V, B plus 1, 2V plus 1 over 6. And those are the only things we need to evaluate this. Okay, so we could do that. I could open up my computer and launch Mathematica, because this is the 21st century. I've got to be a little bit careful because these are general sums. And in Mathematica, I can't sum up to capital N, because capital N is for numerical values. So I'd have to use a different letter. But how could we approximate this sum? And get the main term correct? This is the same as what?
Oh, it's a plus 2n. But each term is a plus 2n.
Yeah, but no, but I'm saying I want a really good approximation. What can I approximate a sum with? An integral. Yeah, this is like a Riemann integral. This is like the integral from n to 2n of x dx. And this is like the integral from n to 2n of x squared dx. And that will give me the main term. And so when I do that, I'm going to get x squared over 2 at n and 2n. And here I'll get x cubed over 3 at n and 2n. And so this is going to be 4n squared minus n squared over 2. So 3n squared, I believe, over 2. And the next one is going to be 8n cubed minus n cubed over 3, which is, I think, 7n cubed over 3. So if I put everything together, it should be approximately 3n times 3n squared over, so that should be 9/2 n cubed minus 2n cubed minus 7/3 n cubed. But minus 2 Oh, wait, the first one is n halves, really? Oh, shit, all right. So we should, what's the common denominator? 6. So I'm a little bit worried that things are not going to come out perfectly, but so if I do things in sixes, this is going to be 27 sixes for the first one. And the second one is going to be minus 12 sixes. And the last is going to be minus 14 sixes. So that's 1/6 n cubed. Okay. It's supposed to be 1/3 n cubed, not 1/6 n cubed. I find it fascinating that we're off by a factor of 2.
I mean, don't we have the lower one?
Yeah, yeah.
So it's
I'm recounting the.
like half of them are of.
Oh, good, 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 excellent. Yes, beautiful, beautiful, beautiful. And then cultural reference. Wait, -1 for the Hebrew God.
What is
Anyone?
that?
Indiana Jones.
Only someone.
So that was the first one. In the fourth one, they wanted to film a motorcycle chase in a library, and they wanted to use the main library at Yale. Normally, you do not allow motorcycles to go through the main library, but if it's Steven Spielberg and Harrison Ford, you know, we can make an exception. So then good, times 2 for the other case, and that gives 1/3 n cubed, which is exactly what I claimed. And so instead of doing these estimations, we could have done it like this perfectly. Another way of interpreting what we've done is we're actually calculating the volume in a certain space. And so you can represent these in terms of integrals. But this is, it gets more and more involved as you get more complicated configurations as to what do they contribute. We were able to prove that the moments grow slower than a Gaussian by a good amount. But they grow fast enough that you have unbounded support. So, there was a lot of stuff we were able to do. And so what we looked at, we conjectured this in the first paper and proved in the second. If you make the matrix a palindrome, so initially it was, B0, B1, and so on. If you end with B0, B1, why is this a good thing to do? So if you go back to how the matrices are defined, how many times do you get a B0? N times. How many times do you get a B1? And -1 times. And how many times do you get a B and -1? You're discriminating. You're not letting all random variables occur the same number of times. If you make it a palindrome, then rather than writing B n -1 in blue, I now write it in green as now B1, and now that occurs n times.
Or would that be 0? And then be input sometimes?
Oh, yeah. Up to an index being off by 1 unit, yes. But if you do it like that, you then wrap around, and that fixes all of the issues. And so, yeah, I can actually just erase like this because it won't let me erase the picture, which is nice. And so if we do a palindrome, it fixes all of the problems because before we had, I plus k minus j had to be between 1 and n, and sometimes it didn't work. And so if we were matching, B1, we had to match that down here. But now this gives us another place where we could match it. And that extra matching, it turns out it fits everything perfectly. And you end up getting a palindrome. You end up getting a Gaussian. All the things that you're missing, you get exactly the right number to fix things. Now, do you notice anything about this? Yeah, now did you actually notice that, or is there this text over in the bottom that says, note the bump at the 0th bin?
I mean, if the axis was like a different color, I would notice it on the graph.
Right.
It's like kind of hidden by that.
So it is kind of hidden, but there is a little bit of a bump there. And so whenever you're looking at a picture, you always want to try to figure out where is the meat, where's the story? Is there a deviation? If there's a deviation, why? Is there a trivial reason for it? Did I show in this class the map of who was rooting for the Patriots in the Super Bowl against the Rams? So there were only 3 parts of the country that were rooting for either rooting for the New England Patriots or rooting against the Los Angeles Rams in the Super Bowl. Did you have the image?
I'm trying to.
Okay. Can you think of what parts of the country might be rooting for the New England Patriots? Yeah, New England,
Yeah.
but only New England. The rest of the East Coast was rooting against New England. And then you need to know some football knowledge for the other 2 parts of the country. Right, and so let me go to Zoom. So when you looked at the map of the US, it was basically, so rooting either for the Patriots or against the Rams, you had New England,
Yeah.
you had Louisiana, and you had St. Louis. So these were the 3 places. New England rooting for the New England Patriots, that's not that hard to explain. St. Louis was rooting either against the Rams or for the Patriots because the Los Angeles Rams used to play in St. Louis, and people were pissed that they had moved to Los Angeles.
What was that? Like,
They were still in St. Louis when the Patriots played them in the Super Bowl in the early 2000s.
oh, okay.
And the last is the Rams made it to the Super Bowl by beating the New Orleans Saints in an NFC conference game where the officiating was so bad, the officials missed a penalty that would have basically given the game to the Saints, that the NFL had to issue an apology after the game saying, yeah, we really blew that one.
That's what.
And they were so pissed in Louisiana that a lot of them did not watch the Super Bowl. They actually reran old New Orleans Saints Super Bowl games.
I mean, that's fair.
But this is the point, is when you're looking at data, you want to try to find out where's the action happening. You know, in a map like this, why is this little part of the country? There's got to be a story. There's got to be something interesting going on there. When we're looking at this map and we see a blip over here, I'm serious. This is what I want you to get out of today's lecture. Something is going on. You've got to explain that blip. So anyways, this is a class on mathematical writing. You can drown people in equations. That's not the goal. You want to try to figure out what do you want to highlight, what do you really want to discuss. I have the image stored. I will send that to you.